Yes, hello everyone. Today we're going to learn more about this instrument called as USM 35. This is used for ultrasonic testing. So what we have here is USM 35. And you have some knobs over here, some buttons here. We'll discuss one by one. What are these buttons? So let's start with the leftmost knob. So you can see I can rotate the knob. See what happens when I rotate the knob. The value here changes. This value is gain, and the unit for this one is dB, decibel. So you can see if I can increase the gain or decrease the gain. Same way on the right side, I have a knob. This is for increasing the value of whatever shown here on the right side. So the range is selected here because you can see by default range will be selected. If I just rotate the knob, you can see the value of range is increasing. Same way, if I want to increase the material velocity, I'll just press this button and you can see the value changes. Any value if I want to change, I can just easily change with selecting it and rotating the right knob. Now after this one, let's go for these function buttons. So this is step button. So you can see if I press the step button, this gain incremental value will increase or decrease. So 6.5. So if I just rotate this knob just for a small bit, the gain will increase by 6.5. You can see. So same way, if I reduce the step size, something like 2, if I increase the knob one time, you can see it's increasing the gain value by 2. Second one is freeze. If I press this one, this section, the graph will freeze off. And then you have save, copy button and enter button. We'll deal with this button later on. Now on the bottom side, we have some buttons. This is for selecting these options. And whatever I'm selecting, let's suppose I press space, I will see this set of functions. If I say pulsar, I'll get settings related to pulsar. Receiver, I get this kind of settings. So you can see receiver, A gate, B gate. So whatever I'm selecting here, the settings will appear here. So this is first level. Now if I want more option here, I will select this button. You'll get some different options related to calibration, reference, trigonometry, memory and data. So, and if I press again, I get some more functions. So we'll be sticking to this basic functions for today. We'll discuss more about the related other functions later on. So first thing first, what you need to do is you need to just plug in the adapter for 12 volts, and then you have to, here you can connect the probes. So the blue and the black one is for transmitter, one is for receiver. So let's get our probes. Hello. Now I'll try to show you the probe. So this is a probe. So this is a normal probe. We can see a normal probe. You have a wear plate on here. Inside you'll be having element, and you have this LEMO connector. You can connect it, and you can see it's having a frequency of 4 megahertz. So let's try to connect it. Here it's very easy to connect. Just press this one in, and it gets connected. Same way, we have a LEMO connector. This is a LEMO connector. So just connect it to any place. So you can just connect it to the black one or the red one. It doesn't make, because this is single probe, single element. So after this is done, what we need to do? First thing first, we need a calibration block. So whenever you're doing any experiment on ultrasound or using any kind of machine, you have to do some calibration. So let me move the machine a little bit back. Here is a calibration block. This is called as a V1 block. So this block will be using for calibrating the normal probe. The normal probe sends the sound in straight direction into the material with zero incident angle. So what we need to do, we need to focus here. We need to adjust this P delay, or sometimes called as probe delay. So what we are trying to do is first set the material range, material velocity, and then go for P delay. What is range? Range is the amount what you are testing. Let's suppose I want to measure a length of, for example, 100 from this top to this bottom is 10 centimeters. If I want to test this 10 centimeters, so I should have a scale here showing 10 centimeters. So you can see clearly here on the leftmost corner you see a 0 and the rightmost is 319. Why you are seeing this one is the range is set to 319. Now if I want to check a length of more than 300 or 400, so I have to increase the range. So let me just press on this one. How do I increase it? Press on range. Now this one is selected. You can see it's showing in white color. Just increase it. As you keep on increasing, we can see the range value here increases. So let me just reduce it and make it something like 100 or maybe 200. So I'm keeping a range of 200. That means I can measure a maximum length of 200 millimeters. Now let's go for material velocity. Sound travels different in different material. But today I'm trying to measure what is sound velocity inside a steel. So sound velocity of steel is 5920. So if you just scroll here, you'll get some reading 5920. This is the material velocity. Now we'll go for P delay. D delay is display delay. So we don't go for display delay. So we can just see what happens if I just press the D delay and change it. We can see it just moves the graph from 0. You can see starting position, it will change. So you can see what it does is it just moves the graph from 0. I can start from 2 to 20, 30, 40, whatever value I gave it. I can even go in minimum side, maybe till minus 10 mm. So just make it to 0. That means we are starting at 0 point here. Now before you do anything, before you do the testing, just set the P delay value to 0. But what is P delay? Probe delay is something like you have this probe. Now the probe element is not till this surface, it is inside of it. So you have some extra material just for cover up, something like a wear material, just as a protection for the element. So that thickness we want to measure actually, and we want to measure and we want to remove that thickness in measurement. So how do we do it? First things first, let me just, okay. So here you can see whenever you are doing ultrasonic testing, make sure you're putting some oil over it. Oil or water or gel, any kind of thing you can use it. This acts as a couplant. If you don't put it, you will not get any signal. Like I'm putting here, let me increase the gain. So you see a very small signal if I don't use any oil. But if I use oil, I get a very good signal. You can see. So that's the advantage of using an oil. So I can just see what I have here. So, but I see a peak over here, but what is the value? So I cannot get the value from here. It's very rough. I can roughly say that it is almost 100, but I'm not sure. But how to be sure? How to get the exact value where you see the peak? So for doing that, we have something called as gates. We have two gates, gate A and gate B. We'll be using only one this time. So if I press gate A, it's saying A gate is off. So you need to switch it on. So select this one and switch on. Once we switch on, you can see a red color line over here. This is called as gate. And whenever this gate red line is crossing the peak, it will give us the value of the top. I mean, the exact peak of the curve. So that's it. Now I can move this gate left or right to select any kind of peak. Let's suppose I want to select what is this peak. I can just scroll over here, or if I want to increase the size of this one, I can increase the size of the gate. So even height, if I want to increase, I can increase the height to select the top peak or bottom peak. So this is a gate. Now I want to go back to the base settings. How do I do it? Press this button to select base. Now whatever value for this gate you're getting will be shown on the top side here. Sound path of 102.5. S is sound path of A gate. SA means sound path of A gate. So now we'll be going for P delay. Select the P delay and just increase the P delay. Now we know the thickness of this block is exactly 10 centimeter or 100 mm. So it should read me 100 mm, but it's reading 102. Why? Because you have 2.5 mm of wear plate on this one. So for doing this one, just you have to use two hands, one to hold this thing firmly, and the other hand you need to just increase the value of P delay to make it 0. Just try to scroll and get the value of P delay as, this sound path value as 100. So now I have a sound path value of 100. Now you can see the peak value corresponds to a sound path of 100 mm. 100 mm means we are good to go. So let me just make it exactly 100. So this is 100 now. Now this probe is calibrated. So these are the steps. First step, go for the range. Second step, material velocity. Then go for P delay. Now whatever length I measure with this probe, I get exactly same kind of result. Let's, for example, here the thickness of this block we can measure using a vernier caliper is it's something like it's 25, almost same like 25. So maybe we can see here, yeah, it's 25. So now I'll try to measure the thickness of this block. Just take this block. So wherever you're keeping, just put some oil. Just 1 or 2 drops of oil. Now if I just press this one, now I'm getting so many peaks. What are these peaks? These peaks at each 25 mm distance, you're getting peak because the sound will go up and down, up and down. It will bounce off like a ball. So let me just reduce this gain. You can see what's happening. If I increase or decrease the gain, the peak value changes. So I just want to check if this reading is 25. But how do I check it? I just see 0 here, 40 here. Now I have to use something called as A gate. So I'm selecting A gate. I'll just go for start position. Just bring it to the first peak. Now the value is showing as 25 point something. So that means my probe is calibrated. Almost. I have some small error, but that's okay for me. Now the second peak, what I'm getting, should be at 50. So let's try to check that one. So here it's 50. I'm getting correct answer. Second one, third one will be 75. Now you can see it's the A line, A gate is not cutting this one. How do I make sure it's cutting the peak? I can reduce the threshold, and you can see now the A gate is cutting this peak. I got 75. So each interval is something like 25. So this proves the horizontal linearity of the system. That means each step of this peak is 25, and the machine is accurate. This is the method of checking horizontal linearity of the machine. Now we'll go for vertical linearity of the machine. So for checking vertical linearity, what I have to do is I have to move this A gate back to the first peak. So I'm back here. Here you can see this total length is 100. So what will be 80%? 80% is somewhere here. So I'll just try to increase the gain value so that the peak becomes 80. Almost 80. Now for vertical linearity, what you're trying to do is we are trying to check the gain amplitude. I mean, if I decrease the gain by 6, this graph should reduce by half. That's how we check vertical linearity. So as you can see, now the gain is 40. If I just make it to 34, we can see it's becoming half. If it is becoming half, then this is a check for vertical linearity. You can check one more time. This is the size of the peak. Increase it, it became double, almost double. Just check it. So that's it. You can actually, this is vertical linearity. Now we'll go for some other properties of checking the probe. Now let's go for checking the sensitivity of the probe. For sensitivity, we'll be using this small hole. This small hole, I think its size is 1.5 mm diameter. So I just want the machine to sense this hole. What is sensitivity? Sensitivity is how sensitive the equipment is. So for checking this one, I can just, what can I do? I just want to make the range less so I can have a clear idea, something like 120. Now I'm getting two peaks. Now I'll be using A gate, and maybe I'll decrease the size of this one, move it a little bit on the top side. Now it's showing a peak at 13.5 millimeter. Now let's try to check that one. So I have with me a vernier caliper. So if I test this one, how much I'm getting something like 14 or 13.5, almost like 13.5. So if I try to measure this one, yes, it's almost like how much I'm having. It's almost 13 or 13.5. So the instrument can measure a small hole of 1.5 mm easily. So just how do we do it? Just move the probe. Once you get a highest peak, just stop over there, or minimum value, whatever you can. It's 13.5. So this proves the sensitivity. That means I can measure a defect of 1.5 mm easily. Now let's go for resolution. For testing resolution, we'll be using this side of the block. You see something like a step here and a notch and a step over here. Now the dimension of this one is different. Like, let's try to measure it. So if I measure this length, this length comes as 91 mm. This one is 91. If I go for the notch, the smallest notch, the distance is 85, and the biggest one is 100, that we already know. So now what we have here, at a small region, I have three different lengths: 100, 95, and the notch one is 85. So what I'll do, I'll just flip this one, and at exactly opposite somewhere here, I'll try to put the probe. Now if I put the probe, I should see three indications for it, three peaks for it. So if I press over here, I should be able to see three distinctive peaks. So let me see. Okay, so you can see if I just move it, you can see now I can easily see these three peaks. That means the resolution of the equipment is also good. We can proceed for the testing. Now if the resolution is bad, you will see something like this: three are combined together to form one peak, but that's not happening. This probe is able to sense each of these thicknesses or lengths separately, and you see three peaks. Now if I would just want to check using A gate what are the lengths. So let me just move the A gate to the first peak. Now you can see A gate is very big compared to the peaks, so I can decrease the size of A gate. So gate size, I'm reducing it, moving it to the first one. Threshold, let me reduce the threshold. So first one I can read as 85. Second one is 91. And the third one is 100. So this proves that we can sense all these three holes together, three thicknesses, they're closely together.